As a case study, let's consider a peel test for a 2-layer laminate. Of course, this could be any other material combination as well. Let's consider that you are doing a peel test with 2-layer laminate, which looks like this. You have an initial crack length and at the interface between the two plies. Let's say the thickness of each ply is h, so the thickness of this sample is 2h. You have a certain length given as L, and the initial crack length is given as A. Now the reason why I write these terms over here is that this is the standard terms it's generally used in formulation of the cohesive zone models. Now for the peel test, we need to apply two forces, upwards and downwards, so as to create the peeling condition. Now this is specifically a mode 1 peel test where you have pure normal loading. You have two layers here which have the same material. So therefore the same material properties. The discretization will be carried out by using bilinear elements because we are considering a plane condition here in X and Y. And there will be a structured mesh, and specifically you would have cohesive elements along the layer interface. So that means you have cohesive elements over here depending on the mesh size all along the interface. Now by means of material tests, we have determined that the fracture strength of this material, which is generally related to the epoxy in this case, is known to us. It's given in Newton per square meter, and the fracture toughness is also known to us. So these are the common terms that you require in order to set up your cohesive zone interaction, which are the inputs required for your traction separation curve, which is given here as GC, Newton per millimeter or Newton per meter. Now, this, if you go back to your traction separation law example that I showed you, this would represent the fracture strength, and this area here would give you the fracture toughness. So these are the important parameters that you require for setting up your cohesive zone model. Now, cohesive zones are going to be introduced only along the layer of the interface because, as I explained before, that is the only location where the crack can propagate. The initial crack length A is very important and needs to be there for the peel test. Material tests are extremely necessary so that you can get these two inputs that go into the model. So these are the three things that you require before you can run any analysis or even prepare a model for prediction of fracture in any structural situation. Now let's say that the crack tip will appear at a certain location. The crack tip is of course going to occur in the first step at location A over here, which is going to be at the end of the crack length or initial crack length, which is already introduced. Now, when the crack tip appears over here, if the mesh is not sufficiently fine, then local softening will occur, causing a sudden release in energy or a snapback behavior, and we will get a failure towards convergence. So the mesh therefore has to be sufficiently fine, causing large computational effort to be spent in solving this problem. Now let's look at, if I carry out a finite element analysis for this particular model, what would my result look like? So let's say I'm looking at a shear force, which is given as tau, shear stress tau xy, and I have the displacement here delta y, the y direction. And what I would see is that in the beginning, there's of course a linear part where we will reach the limit point. Further, you will see that you will get some kind of oscillations which will change slope over time when the analysis completes, right? So now I can relate this result back to what I already said before about what happens when the crack tip appears and the mesh dependency. So let's say that this is first model where the mesh is not sufficiently fine. So what we see is that you have a limit point over here that becomes clearly visible in the analysis. In this condition, if you look carefully, you see that because the mesh is not sufficiently fine, you will have local softening of your material. You will have a sudden release of energy. So you see here that it increases, but at the same time it goes down quite large and quite in a very short span. And this is the snap back behavior that I was talking about because of this softening and sudden release in energy. So if such a situation happens and the mesh is absolutely not even close to being processable, then you would have computational problems and your analysis will terminate over here. However, in this case, of course, the mesh is not as bad. Therefore, you will have localized softening. So you will have snapback behavior, but it will also start moving towards hardening. And then you would have again release in energy and again a snapback. So you would find convergence somewhere here eventually. However, there is of course going to be these large oscillations which are related to local snapback because of material softening and of course related to your element size. Now another important attribute of these results, of course this is just a representation of the actual results, but you would see that they are quite close to how you would see. Now here you have very high oscillations. And as I said, these high oscillations can be reduced by refining the mesh, which lead to higher computations. Another thing is that the snapback occurs because of material softening. So this is material softening behavior. If I draw slopes of these material softening behavior, you would see that here the softening happens to be much sharper. So the slope is much higher. However, when you move on, the slope becomes less and less. So the KT, the tangent stiffness slope, is reducing gradually as the analysis moves forward. And this is the effect of material softening. So what we are doing here is that we are able to reduce the stiffness of your material because by taking into account the traction separation law that we looked at before. So of course these results relate only to your cohesive zone where you have these specialized elements introduced. So in a nutshell, you need to have a fine mesh, and when you have a fine mesh, you would see that your results are going to change. And instead of having such large oscillations, you will have smaller oscillations. The material softening nature will still be very clear because of the lower slope of the KT. And you would have very high computational steps required before you can get a converged result. The mesh refinement is obviously going to reduce the oscillatory behavior. So keep that in mind when you're working with cohesive zones. How can you improve your model further? You can improve your model further by making some observations based on previous examples or literature or even experiences that I can share with you. Now, some observations that we can clearly identify are the use of linear elements may be insufficient. Linear elements have insufficient approximation properties which further enhance the oscillatory behavior. So it is better to most likely use higher order elements. So avoid lower order approximations. Now, second one is that crack propagation is due to increased displacement of nodes. Therefore, a lower number of nodes may overestimate the crack behavior or the crack length. For example, let's have a look at this cohesive zone. Let's say we have these are the nodal locations which are shown by circular shapes, and you have a crack which has opened up in this direction over here, and there's further crack opening ahead. Now, nodal displacements are caused to create further crack opening. So this is the next step that is expected to occur for crack propagation. Now, if in case the actual behavior should be as shown with the green curve, you are not able to get it because the number of nodes that are present are insufficient. So if we have lower number of nodes, then we also may overestimate the crack behavior or the crack length, because this is related directly to the fact that if you use a certain element edge length, that defines the number of nodes that you're using. And hence, if you have a smaller edge length, then you can introduce more number of nodes, or if you are using higher order elements, you also introduce a maximum number of nodes which are able to deform better to give you a better estimation of how exactly the crack will open closer to the experimental behavior that you would observe in your material. So we come back again to the first point, which is linear elements may be insufficient, and of course further backwards, which says you might need a finer mesh. Now, if I have lower number of nodes, which it also means that the forces are going to be higher than actually needed to open the cracks because a longer edge length is involved. Yeah, so if the load increases, you can have further accession of fracture strength, which is also overestimating your results. Higher elastic deformation can occur if you have a further accession of fracture strength, which means that if I have nodes that are further apart from each other, I have a higher load or force which is required to open the crack, which also means that the local softening behavior that we saw in terms of oscillations will be much higher, causing higher size of oscillations with higher elastic deformation for energy dissipation. And therefore, the decrease in traction separation curve or decrease in the slope of the traction separation curve will also occur. So, all in all, moral of the story is that higher order elements may work better, but a combination of a refinement of the mesh along with the use of higher order elements will lead to a smaller number of elements, less number of load steps, also with the possibility of adaptive refinement only within the crack propagation zone will help improve your model. As a final conclusion, I'd like to show you some results of the field test that we discussed with some of the different options that have been used and different ideas of the mesh refinement, etc. that were taken into account. Now, if you look at the one which is on the top right, you would see that we started off with, I don't know if it's very clear. Now these, then of course they look like bilinear elements, but actually they were higher order elements which had nodes also along the edge. Therefore, you can see that you can have crack which can propagate to the node which is present midway through the element as well along the length. Now, in order to make sure that we have a good result, or we are making use of the right number of nodes, we are also going through adaptive refinement. And if you can look, I don't think you can look very closely into this, but the maximum number of elements that it has been, one of the larger ones has been divided it along the length into are more than about 20 during adaptive refinement. Therefore, we are able to move from one node to the next node without causing any computational failure or very large oscillations in the results. However, it took a very long time to run such an analysis. If you are able to look into the point of the third one or the fourth one over here at the bottom right, you can see that here the size of the model is smaller. So we started off with a small element length, but at the same time the propagation has happened over smaller element length, and the results are actually much better in this case than in the case over here. Of course, I can't show you the results here, it's part of a different study, but the idea to show you these kind of results is that it's always important that if you have certain crack lengths, because this is the case of a zipper, so these places do not have material, so material has been removed in these areas and these circular parts to make sure that we are going to propagate the crack along this length. So it is going towards the point where you do not have any more material, and therefore it's an easy path to follow.